Should probably start. Can everyone hear me fine? Cool. Right, so RAGtime with Postgres. Again, trying to break the longest presentation title record. AI power with pgvector. So, this is, of course, Scott Joplin. He is the king of ragtime music from the 1800s. But we're not talking about the music genre at all in this presentation, so it was just a pun. We're talking about Retrieval-Augmented Generation, and we'll get into what that means in a moment. First of all, let's talk about the hype, right? Whenever you see anything that's AI related, the hype is overwhelming. So you've got buzzwords like LLM, GPT, vector databases, you have AGI, the mythical AGI, general intelligence. MCP means API, basically. They could just say API. LangChain, AI agents, agentic AI, which is different to AI agents. And we in the Postgres world also have our own hype and buzzwords. We have data lakes, we have warehouses, we have lake houses, we have, yeah, nice to spend the weekend in. We have serverless databases. Yeah. So it's reasonable that all of these buzzwords and claims are met with skepticism. Some of the skepticism is really harsh, right? Some of the criticism. Professor Ulises Mejias of State University of New York says, as we learn about how the technology works, we realize that generative AI is nothing but statistically derived plagiarism, which is kind of a hot take, but when you've got proof on your side, it kind of mars the whole image of AI. So is it like AI is bad, is useless, it doesn't deliver what it promises? No, not exactly. But on the other hand, it's not the panacea, right? It doesn't fix everything.
Their lawsuits are pending.
Yeah, I will. So, what is the answer to the hype? The answer to the hype is building practical tools. Only if you demonstrate the value of these technologies that have been built with practical tools that actually make a difference in someone's daily job or society, then you'll deal with the hype. No. About me, I'm not an AI expert, right? I'm making that very clear from the start. I'm just a Postgres nerd. I'm a systems and database architect. I'm based in Edinburgh in Scotland. I've been an open source user and contributor for 25 years plus. Out of those, I've used Postgres exclusively as the only database I'm working with for 17 plus years, and I am a contributor to the PostgreSQL project. I'm a member of the Postgres Europe Diversity Committee. I've written a couple of books. The latest one is called PostgreSQL Mistakes and How to Avoid Them. I've co-authored the Postgres 16 Administration Cookbook, and I have written a Postgres extension for the collection and visualization of internal statistics that's called pgStatViz. Now, what we'll go over is the what, right? What is RAG? Why you would need RAG? How to do it with Postgres? And then we'll look at a specific real-world problem that we will then solve by building a RAG application. And then we'll see a few tips where that would have been helpful to know before I started building this thing, and some caveats that also would have been helpful to know. So, what is generative AI? Generative AI is basically a statistics term. when you have a generative model which can produce pictures, audio, video based on statistics of previously learned images or words or videos. So that's called a deep generative model because it has performed deep learning on its training material. And it's usually trained on all of the commercial ones that you see, the hype is around, is usually trained on a large corpus of copyrighted works. And as you kindly pointed out in the audience, lawsuits are pending for this sort of thing, so people don't want to comment on it. What are LLMs? You may have heard the term. It's large language models, and they're basically deep neural networks for language-based tasks. And they utilize a technology that's called GPT, which is a generic term and shouldn't be copyrighted because it means generative pre-trained transformer. So that's the methodology they use to generate these objects, these texts, these audio files, these images, and so on. And pre-trained is the key word here. These models are static. They're not dynamic. They have been trained on specific data sets, and they can only produce stuff that is close to what they know in their data sets. Now, what's the problem with LLMs? LLMs can lie, like blatantly, outright lie. They make stuff up when they don't know the answer. And people have started realizing this. And they can also hallucinate, which is the politest term that I could find for this presentation. It anthropomorphizes software, and it's really not the proper term. Also, another problem is that their knowledge, because we said they're trained on specific data sets, their knowledge is frozen at the time of training. They don't know anything newer that's come out since then. And of course, because they're static, they get progressively more stale as time goes by. They also know nothing about your use case. They don't have access to your data. So if you're telling it to, come up with an answer for your problem, you have to provide the data as well, because otherwise it doesn't know anything about your use case. And finally, they seem to be suffering from something that I'll call commonness bias, because the term doesn't seem to be in use. It's a mixture of the availability heuristic and the Einstellung effect, which basically means that the more familiar something is to the LLM, the more likely it is to hallucinate responses that are relevant to that thing. I'll give you an example. If you ask these commercial models that are available now to tell you something about Apache Pulsar, 99% of the material they've been trained on is about Apache Kafka, which is a very similar technology. So like 90% of the time, you'll get answers relating to Kafka that are wrong and are hallucinations when you ask it about Pulsar. That's one real-world example that I stumbled across. Any Eurovision fans in the audience? That was a song from Eurovision this year. This is a screenshot from today, actually. It's really fresh. I asked Claude how I can tune the toast compression level in Postgres. And of course, this parameter doesn't exist, but it tells me that there are multiple ways to tune it. And here's one, and then you have to select pg reload constant or restart Postgres, which has nothing to do with reloading the configuration. Right, so this is super fresh. This is the current model that people are trusting their code with. They're vibe coding with this thing. Cool. What is RAG? RAG is Retrieval-Augmented Generation. What does that mean? It means that it incorporates information retrieval in the LLM response generation. So this addresses the aforementioned problems. It reduces hallucinations because the data is more relevant, and the data is fresh because you're pulling it straight from a live database in most cases. So what it's doing is it's supplementing the information that was missing from the LLM training data to your prompt. And that way it can give you a better answer. It's like an open book exam for the LLM versus a closed book exam, which is without the retrieval. So what can we use, what could we use for information retrieval? This is the Stack Overflow 2025 Developer Survey has just come out, and Postgres is like way in front of everyone else for the third year in a row as the most admired and most desired database. Let's see what the survey says learners specifically in the AI field are using. They seem to be using MySQL over Postgres. Let's see what professionals use for AI, according to the survey. And the survey says 60% Postgres. You will notice that the vector and AI databases are conspicuous by their absence. Anyway, back to RAG. How does RAG work? The secret sauce really is called vector embeddings. They're also known as word embeddings. And it's basically encoding of words into vectors of real numbers. So if you can visualize it, let's say, in 2 dimensions. Let's say we have the dimension of age and the dimension of gender, and you get this lovely graph that Dave Turetsky has provided in his word embedding demo. This is called distributional semantics, where words that are closely related in one axis are clustered together. You can, of course, have more than 2 dimensions, and this whole thing is what allows us to search by concept, not just keywords. Let's see what the stages of RAG are. First, you have to start with the indexing, which is converting the text input using what we call an embedding model, which isn't the same as your large language model, because it's supposed to do a different thing. It's supposed to group these semantically and extract the words from the documents that you feed it. And then you store the embeddings that the embedding model generates in a database. And it's as simple as that. The next stage is retrieval, where your user query retrieves the most relevant documents to what you have just typed in from the database. And then the next stage is augmentation. So you take your original prompt and you add to it the data that was fetched from the database in a way that makes the prompt more useful for the next stage, which is generation. And that's the generation of the response by the LLM. Now, how does RAG work in Postgres? Your friend is pgvector, an extension that you can load. It adds the vector data type to Postgres, and you basically store the vectors as a simple column in one of your tables. Yes?
Can you describe why that was possible with PostgreSQL?
Yeah. So the question was, why was this possible with Postgres? Because Postgres is by nature extensible and extendable. You can create any sort of data type, you can create any sort of operator, you can add functionality to Postgres in a very easy way, and that easy way is called extensions. Because you don't have to go through the main development workflow of the entire Postgres project to get this feature added. Someone needed it, they wrote an extension, and by someone I mean a group of people and companies that have contributed time towards pgvector, and that's why we have this functionality available to us now. And equally, if you don't need vectors, you don't have to have a bloated database that includes all the things you're never going to use, right? So this is what extensions help with. Now, after you've put the vectors in the database, that's the good stuff. You can store the embeddings alongside your original document, unaltered, and other metadata. And we'll see what metadata was useful for my use case. So basically, you type in create extension pgvector, and that enables the extension if you've installed the packages. And normally, you just create a table, let's say documents, the original content as a text column, and the embedding of the content as a vector. And you'll notice that it says size 384, that's 384 dimensions to the vector. So the size of the vector depends on which model you're using. So you have to tailor that column and the dimensions of these embeddings to the specific model that you're using for retrieval. So how does RAG work in Postgres? You just select content from documents because you want to retrieve the original text, right? You don't need the numbers. You don't need a vector of numbers in your prompt. It means nothing to the large language model. So you want the original document. And one way you can do it is you can order by 1 minus embedding. And this weird spaceship operator is basically the Euclidean distance between 2 points or vectors. So you sort it by how relevant it is to the query, which in this case is kind of useless. It's just my query. And of course, you need to convert the query to vector in order to be able to compare vectors to vectors. You can't compare vectors to text. Okay, but isn't this like searching with like? Isn't it going to be slow? Yes, it will be immensely slow, which is why we have indexes that make it very, very fast. So we've got IVF flat is one index type, and the other index type that pgvector offers is HNSW. Now, an IVF flat index can be created like this. Create index on the table that I said, documents, using IVF flat as the syntax. And you index the column embedding with the specifier vector L2 ops. So that will perform L2, will optimize the index for L2 Euclidean distance comparisons. That's what that means. And with lists equals 100, it's because IVF flat indexes divide vectors into lists, and then they search a subset of those lists that are closest to the query vector. So you don't search through the entire field. So that may affect accuracy. A question?
Yeah, if there are other kinds of operators that you want to query on, does this index help with those searches as well?
No. It's only a vector index, and it only helps you.
Euclidean difference.
Exactly.
So if I want to do like cosine distance?
Yes,
Whatever,
that's a different operator.
but I just build another index for that.
No, you can use the same index, but you have to use it with vector cosine ops as the specifier, as the modifier.
Okay, so like vector L2 ops would not help those kinds of queries?
If you are querying on cosine difference, no, you would get suboptimal results. They would be close enough, but it wouldn't be as good as you want.
What's that? What was your question? If I wanted to do queries with the cosine distance operator instead, if I need a separate index to do that,
Right. So the canonical answer is yes, you should optimize the index for the kind of querying you're going to do. Now, let's talk about problems. One,
You said that you need to optimize an index for the type of query that you're going to be performing. Is that right?
yes. So the question is, yeah, do we have to optimize for the type of query yes, for the type of comparison that you are performing for your search vector compared to what's stored in your database. So if the operator you're using is, as in this case, the L2 operator, you would build an L2 based index. If it's a cosine operator, which is the equals sign in between the, then you would need to create a cosine IVF flat index.
The same with all other indices as well.
Yeah, same. Yeah, same. So indexes, yeah, they have to support the specific operator you're using them with.
Speaking about like, you do the search by bit tree with like, but you could build a
Cool.
pattern
Yeah,
option and like
exactly.
with like.
So if the index doesn't support your operator, whatever the comparison operator is you're using, the index will just not be used.
Yes, no how.
You will see it in the query plan. Cool. So, what's a problem we can solve with this technology? Let's say that you have a very large legacy code base. You have millions upon millions of lines of code stashed in various repositories and systems, either deployed or not. What if your code experts that people have to ask about the existing code have left the organization? What if they are too busy with other work? So they can't spend the time, explaining to you how the really complicated code you want to work on works. What if they had actually forgotten what they did 10 years ago on the very important code that they wrote that your entire organization hinges upon? This is real life. These things have happened in real life, all three of them. Possible solution is you can create a RAG system, and the RAG system will be your code expert for all intents and purposes. So what you have to do is you have to index the content of your code repositories, and then you have to create an interface to query this system, this RAG system, which can be a web chatbot like you see on chatgpt.com, for example. That's a chatbot. Or it can be a Slack bot. It can be conversational. It can send you messages. So let's build a real-world RAG application. The workflow looks kind of like this. From the user perspective, from the user/builder perspective, which was my perspective. I was the first user of the thing I built. So first of all, you retrieve code from the repositories. And that basically means looping over a lot of repositories and extracting the code. You generate the embeddings of that code, and you store it into the database. Then, as the user, you enter a natural language query into the interface that you've built. The interface code optimizes the query before it sends it to the database, because you can do some clever tricks here. And then you use the optimized query to retrieve the code snippets from the database that are relevant to the natural language query. After that, you add the code snippet contexts that you've pulled from the database to the prompt that's going to go to the LLM that will generate the final answer for you. So then you send that engineered prompt to the LLM, and all you have to do when it responds is to format and display the response. You get bonus points if you can keep the conversation history going for each interaction, like a Slack thread or a web session, let's say. So cloning the repositories locally. I basically wrote a Python script that cloned the repos. You can do it with from GitHub, import GitHub. You feed it some GitHub token so it can interact with the GitHub API. And then with the GitHub library, you just get your user, and then you loop over the repos that belong to that user. Easy. Once you've got all the files on disk, you can create a database. So you create a table, let's say source embeddings, where you store the repository name, of course, because this code may be spread out over multiple repositories. So you keep track of the repo name, you keep track of the file path, the content of the file, and then, surprise, we have two kinds of embeddings. We have semantic embeddings and code embeddings that we're going to store for this thing. And they have different dimensions because I'm using different models for these two. Created that is, when the file was imported into the database. You can store other things like when the embedding was generated and so on. Git commit is important to tell things apart because if you want to refresh your repositories, you have to know that that file has changed and update the embeddings for it. And I've just gone with a primary key combination of repo name and file path should be good enough for, yes, please.
Is your commit a hash or is it the whole commit message?
No, it's just, the question was if the commit is the entire commit message or the hash. No, it's just the hash of the commit. So you can tell that the file has changed. Even if the commit doesn't change the file, it's kind of silly, but it's one way to be sure. So then you index your repositories. You write a Python script that creates the embeddings in the database for each of the files. So the document is the file, the content is the content of the file. We are using a dual indexing strategy. We're using semantic and code embeddings because that increases accuracy according to my tests. So you can use sentence transformers and auto-tokenizer and auto-model. And the models that I used, a semantic model that I used was free to use from from sentence transformers. I used all mini LM L6 version 2. I used it on a PC with no graphics card, so I specified the CPU device and some other details that we don't need to get into. For the code embeddings, I used a different model from Salesforce that's called T5+, code T5+. And that requires its own tokenizer to break up the code into tokens that are recognizable by the pre-trained model code T5P+. So
Can you review what these vector embeddings are? I'm saying like you train.
so what's the question?
Can you review what those are, what they are themselves?
The question is how you can review what those embeddings, what those training models are.
Right.
Right. So I basically read the documentation. They're all available on GitHub as ready models that you can use straight away. They're pre-trained, and they come with their own documentation. So some of them are suitable for natural language queries. Some other things are suitable for code. So that's why I've used two different things here. Now, you should probably pre-process your code because it improves the quality of the embedding. It has less fluff around it. So I normalize the white space within each line. I removed the comments because they can be misleading, and you don't want the LLM to respond with the comments that it found in the code. You want it You want the LLM to respond with the code that is actually running in production, not what the comment says that the code should be doing, right? So it's a bit of a hazard. That's why I removed the comments. I replace all the string literals because they are irrelevant to the code with a placeholder. And I removed consecutive blank lines. So it's really easy to do these things. In Python, you just use regular expressions. You strip out white space. You strip out doubled blank lines. And you substitute everything that's a string with str. So the model knows to ignore it because it doesn't mean anything. Otherwise, it might pick up on the meaning of the word in the string. And you don't want it to do that. So after you've prepared your text, you generate the embeddings. And you have to chunk, as we say, the content into chunks. It's an imprecise art, so you have to experiment on the optimal chunking size. Generally speaking, for semantic, what you want is overlapping chunks. So you don't want one chunk that only contains these words somewhere in the database. You want another chunk that slightly overlaps so you can find better semantic matches. Because otherwise the chunk would be isolated and wouldn't be related to other things close by in the sentence that you're trying to analyze.
Is this just for, like you said, the sentence model, like the sentence embeddings? This chunking is important for that particular
Chunking is important for everything.
for everyone.
Yeah, so you want to use it. You want to chunk your code embeddings, and you want to chunk your semantic embeddings as well. Why don't I just use code embeddings, right? Because they actually don't give you all that good of a response. Because the code embeddings, the models don't really understand anything except code. So it will respond with code. And you don't want it. You want a natural language explanation that includes code if needed. So the way you chunk it is you set a chunk size. I wrote a function called chunk code for semantic. I specified the overlap, and I just ran the chunking function that was available from the Python model that I used to perform the chunking. And that turns it into a list of strings, which are all of the chunks in your document. For Code T5+, we use smaller chunks than that because it has a limited context window. So I used 512, which was the maximum chunk size that it could handle. And it's basically the same. I just use the tokenizer, and it breaks it up into tokens and chunks. So the tokenizer for the code, of course, I've imported Torch, I've imported NumPy to do some mathematical stuff. You just basically loop over the chunks that the previous function generated, and you pass them through the code tokenizer. And the tokenizer is actually what converts it to embeddings. So to things that are digestible for generating embeddings, right? So again, this is details. So Torch no grad, ignore it. It specifies no gradient for PyTorch, no gradient calculation. So the outputs are the inputs passed through the code model. It's really simple to understand in Python. And then you have to do some manipulation of the output, and you turn it into a NumPy array, and then you append each chunk to that array, the output for that chunk to the array. You then have to average and normalize the embeddings from all chunks because you are dealing with an entire file, right? And you want to generate the embedding for the entire file, not those individual chunks. And this is how it works. You average it out, you normalize the values. This is the boring Python code that does this. And then in the end, after you perform all the averaging and normalizing, you have the final embedding, which is the vector that you're going to store in the database. For the semantic embeddings, similarly, you loop over the chunks in the file. You create your semantic array, and again, that semantic array is really what you're going to be storing in the database as the embedding value in that column.
So you have two loops for different types of embeddings. One is semantic and the other one's for code. But you're using the chunks independently for both of those.
Yeah, yeah, it's inefficient,
No,
but
I was just curious. I just wanted to make that clear.
yeah. So there's two different loops. Just for clarity in the code, because efficiency of generation wasn't important for that project.
Yeah, I was just wondering, I wanted to understand exactly what data is being passed into the encoding aspect for both.
Right.
So it seems that it's the same code.
Yeah, but you have to use different chunk sizes, so you can't use the same chunks for both models.
So you have to chunk it separately, basically.
You had two chunking functions earlier
Yeah.
you showed us. Right?
Yes.
Chunking for code.
Yes, one is chunking for code and the other one is chunking for semantic. So now you have the embeddings. This generator has spat out the embeddings, and you need to store them in the database. So you insert into source embeddings the metadata, right? And you also insert the semantic embedding that you have and the code embedding that you have. This is SQL in Python, so that's why it has the placeholders for the variables there, for the parameters, excuse me. I entered the onConflict clause so that I can update my code embeddings without rescanning the entire thing and reparsing the entire thing. So it only updates the changed things. And the do update clause makes sure that if the row that you're trying to insert with the same repo name and file path exists, then it updates it instead of performing an insert.
So this allows you to update the data in the database, assuming the code base changes, you keep it refreshed.
Yes. This allows you to refresh the data without rereading the parts that haven't changed. And then once you have the embeddings in your database, in your table, you create an index on them. So for this, I've used cosine operations for the IVF flat index, and the same for the code embedding column. And then you come to the juicy part, which is querying the database. And here's where I cheat a little, because I have the LLM that's available to me optimize the query from natural language to something that the other model will understand more clearly. So if you tell it, for example, for the semantic query, it's pretty clear. It's like, how does this piece of code work? Or how do you calculate these functions? For the code embeddings, that natural language query doesn't work. So you have to tell it to generate code that looks like what you've described. So it tries to generate keywords in various languages that match what you've described in natural language. And that is the query that you send to the code embedding. Also, the semantic query is processed. So if you have typos, if you have grammatical errors, it will tidy it up a little bit before sending it to the LLM. So you generate the query embeddings using both semantic and code queries. And those embeddings are the vector that you send to the database as the query. Right? So we're using the embedding models not only to index our data, but to perform the prompt generation for the query as well. pgvector expects XYZ format. I said Z because I'm British. So semantic vector becomes a string that is basically sent to the database as a vector string. It's really simple. Now comes the fun part, which is the SQL query. So I do a thing, a CTE, common table expression, called ranked here. And I select the closest thing as semantic similarity for the semantic data, as code similarity for the code embeddings, and then I rank them by similarity by using this window function, row number over ordered by. And what I do then is I select from ranked the top 20 semantic matches and the top 10 code matches, because I think semantic works better for this sort of thing than code matches, but code matches catches some of the things that semantic leaves out. So it's a combined effort. If by some coincidence those happen to score highly in both, the results appear in both the semantic list and the code list, then they get an extra boost. So they come to the top of the results, because they must be highly relevant to score in both highly. And then you send the augmented query to the LLM, which is basically blah, blah, that the LLM wants to read. And it says, you're an intelligent code assistant with a heavy focus on Postgres. Below you will find the relevant code patterns. Use those patterns to provide accurate contextual responses about the specific implementation, blah, blah, blah. So highly relevant is where I output the boosted results. Semantic matches and code structure matches. And of course, the LLM doesn't know anything about our system, so you have to explain it to it. And then you say you should prioritize high priority results, and so on and so on. Your response should be in Markdown, and you should format any code blocks accordingly. And then you substitute the code context, right, which are the files that you've retrieved, the content of the files that you've retrieved, and you append them to the prompt. That's how this whole thing works. So some sample queries, let's say for an insurance company, could be, and these things work. It's impressive how well it works when you feed it the proper context from the code base. It's like, how do we price life insurance contracts? Which has nothing to do with code. The query you've just input has nothing to do with code, and it actually shows you, it reads the code that actually prices the life insurance contracts and gives you a contextual answer. Or like, what is the method of calculation for additional contract discounts? It is something a developer needs to know. When the product manager comes in and says, we need to add this feature, or we need to rethink how we calculate additional contract discounts, the developer may have not been involved with that code at all. It will save them a ton of time if they ask the code expert, instead of just scanning through hundreds and thousands of lines of code to find the relevant bits. Another complicated system is the Postgres Europe conference system that is being used by the Postgres community to organize conferences. So, for example, if you don't want to ask Magnus, you can ask this thing what the workflow is for adding an attendee registration to the system. Now, some tips. From the application side, I used Fast API to build a web interface, and I used the Slack libraries for Python to create a chatbot that responds on Slack. You can make this even simpler. You can make it into a simple API or even a command line tool. You don't need an API at all to query it. I saved costs by using sentence transformers and other free resources. versus using an expensive commercial API to index your data. Imagine if for each chunk you have to send it to some company's API that charges you per byte. How expensive this can get, especially with increase in your data size. And if your system consists of multiple repositories, if you have a complicated system with code that's in Python and Perl and C and whatever, this tool can give you answers on a system-level scope. It can tell you that this component is talking to that component, and it will figure it out from the code, because it will see what is being generated in one component and what's been received by the other component. So it's basically expert-level answers. The accuracy might not be as good as the person who wrote the code and remembers the code, but sometimes it can even help jog memories. Now, again, you can send your augmented prompt to an external LLM API. In my case, because I had Claude available, I used Claude for my response generation, but that's expensive, and if someone else is paying, that's a factor. Stability is also a factor with an external API, because anyone who's tried to use AI APIs has always is very likely seen this message: this server is overloaded, or the API is overloaded, please try again later, or you have no more tokens left for today, and you don't care, you want an answer. So the reliability is also an issue. Are there any guarantees that the model that is responding at that API endpoint will be the same model tomorrow? No, there are no guarantees, right? You have to take their word for it, because they operate as black boxes. What you can do is you can run Ollama locally and run the LLM yourself. This is best for information security because the data never leaves your system, and of course it's better for cost. What I would use for my chatbot would be CodeLlama 7b Instruct, because Instruct allows it to understand human natural language queries as well, not just code input. The capabilities, though, may not be on par with the commercial APIs, unfortunately. On the database side, I used IVF Flat. It creates the indexes faster. HNSW can give you more accurate results with 100% accuracy, and it can respond faster, but it takes much longer to build the index. So some caveats. First of all, LLMs can generate misinformation even if you feed them highly accurate data. Even if you feed them factually correct sources, they can still hallucinate if they misinterpret the context. Like, I'll give you a simple example. Someone writes a sarcastic sentence. They will take it at face value and respond incorrectly. Now, open source models, like the sentence transformers that I mentioned, Ollama, and all that, yes, they're available, they're free as in beer, but no one has access to the training data because that remains a secret. So basically, they're not open source. They're just free to use, even though they're calling them open source models. And final caveat is a diagram from my recently published book, where I try to illustrate what happens when you load the code into your computer and you run your code checker, your LLM, whatever tool you have. It generates the analysis on that same system. When you use a cloud service like a cloud AI API, then it goes onto someone else's server, and you always have to remember this. And you get the analysis, fine, it works as well as your local model, or better, but basically they can do anything they want that's in their terms of service and privacy policy to your data that you've sent willingly to their server. So that's always something to be aware of. There are organizations with information security policies that prohibit you from sending code snippets to anywhere outside their organization, even if there's a contract with, let's say, OpenAI that processes your data. You can find me on socials as Jimmy Angelakos or Virus. And I have a discount code for my book. If you want to use it, it will give you 45% off of everything on Manning publications. And I am now open for your questions.
Can you review again the input query that generates these semantics and
The input query.
that you tell the LLM, hey, give me.
Yes, the select from the database.
Oh no, the one that you sent to the LLM with the embeddings. Not this one, but the one that.
This is the one with the embeddings. So I'm performing a select based on semantic embedding similarity to the vector.
Right, but this already took from the LLM some information, right?
Oh, you mean the optimization? That happens inside the model. So I ask the model, take this prompt and transform it into something that looks more like code in one instance, and the other one.
When you had a slide that had that query, right? That you passed to the LLM.
You mean like the prompt with the code context?
Yeah,
at the
prompt,
bottom?
prompt.
Yeah. Keep going.
I get you, yeah. The prompt with the, yes. Oh, the whole prompt, the textual description, you mean that I gave it, yes. Yeah. So my instructions were, you're an intelligent code assistant, so that it knows what to do, what to respond with. And then I instruct it to focus on the highly relevant results first, then the semantic matches and the code structure matches. While you can describe the one instruction that I gave it is, you can describe the patterns that you see, do not directly quote the code, because I have the code open in another window. I don't want to read it again. So unless you have to illustrate something specifically with code, don't show me the code, was one part of the prompt.
I see. So then the two embeddings are only provided to essentially allow you to pull the more relevant snippets of code that you're going to use.
Yes, the embeddings are sent to the database. The prompt is transformed into an embedding. And then you can compare that embedding with the embeddings that are stored in your database. And then the results are placed in here inside the prompt at the end, as I've explained to the LLM. There's nothing else. Thank you very much.